Our project title is Comparison of the Complexity and Quality of Feature Reduction Techniques Used in Data-Dependent Feature Extraction. Suppose we want to classify cell phones. We want to distinguish between an iPhone and a Samsung phone. There are so many different features distinct to each phone that we can look for. But we don't need all the features, right? We can just look for the Apple logo on the back of the phone. We just need one feature. This is called feature reduction. So the problem in our project is classifying handwritten digits. We use MNIST handwritten digits that are originally 28 by 28, but here, for the sake of simplicity, we have reshaped them into 8 by 8 pixel images. Obviously, we have 64 features here, and that is a lot. What should we do? What method should we choose? Which method has the best performance? And which one is the fastest? So, there are many feature reduction techniques out there, but here we have focused on some main nonlinear embedding methods that are isomap, LLE, modified LLE, Hessian-based LLE, LTSA, MDS, and TSNE. These are the softwares and hardwares that we have used for this project. We have used the PyCharm IDE. Also, we have used the scikit-learn package for the implementation of the embedding techniques. All simulations have been run on MacBook Pro 2021 with M1 Max CPU and 32 gigs of RAM. Now I want to show the simulation and program coding. As I said, I have used PyCharm and scikit-learn packages. As you can see here, I have used some packages, some regular packages, but the scikit-learn package, and I have imported the methods, the embedding methods, isomap, LLE, MDS, TCNE, and some others. I have loaded some digits, and as you can see here, I have imported the embedding methods. And finally, I have done the embedding and plotted the projection. I will run this now. You can see the first 64 digits from the 8 by 8 dimensional digit datasets here. And this is the projection that I want to talk about in the feature slides. So the runtime of each algorithm mainly depends on the complexity of the algorithm. The complexity formula of each algorithm can be reached at section 2 of the project reports. There are some implementation details that we need to note here. As mentioned before, the input feature dimension is 64, while the output feature dimension is reduced to 2, obviously by the embedding techniques. We set the number of nearest neighbors to 30. Also, for the TSNE algorithm, we have initialized the algorithm by an embedding generated by a PCA to ensure its global stability. For the MDS method, the maximum number of iterations is set to 100. Okay, we start with the worst method and go to the best. The worst method for this problem is the LLE method. LLE can be thought of as a series of local PCAs which are globally compared to find the best nonlinear embedding. The standard LLE is a fast algorithm. Actually, it's the fastest among our methods here. The performance is poor though. As you can observe, LLE method is not successful at all on 5-digit datasets and has only managed to classify digit 6 on the 10-digit dataset. The total complexity of this algorithm is not that high, but the bad performance is enough to give it a C grade. This one is an average algorithm in our list. MLLE. One method to address the regularization problem of LLE is to use multiple weight vectors in each neighborhood. This is the essence of the MLLE method. We can see that this method is successful on distinguishing digits 0, 1, and 4, but is still not doing that great with digits 2 and 3. For the 10-digit dataset, the distinction problem between digits 2 and 3 is much less severe, but digit 9 is scattered all over the embedding plane. The runtime is slower than the standard LLE and isomap methods, but the performance is much better than the standard LLE. The acceptable performance and average runtime are why we give this method a B grade. The next one is HLLE, Hessian-based LLE, is another method of solving the regularization problem that LLE had. As you can see here, in this problem, this method performs almost identical to the last one, the MLLE method. It is slightly faster than that one, and the total complexity is almost the same as LLE and MLLE. The acceptable performance here and the average runtime is why we give this method a B grade. The next one is also average and is isomap. Isomap seeks a lower dimensional embedding, which maintains distances between all points. As you can see here, isomap method has done a good job on classifying digits 0, 4, and 1. However, digits 2 and 3 are almost non-distinguishable in this projection. It gets worse for the 10-digit set, as the problem with digits 2 and 3 still stand, and there's almost no distinction for digit 1, since it has been mistaken with digits 2, 3, 5, and 9 in multiple cases. The runtime, however, is not bad at all compared to other methods. The isomap method is an average method compared to others, but it is not advisable, since it literally does no distinction between digit 2 and 3, so we will give it a B grade. The next one is our honorable mention. It's LTSA method. LTSA is not technically a variant of LLE, but it's very similar to LLE that it can be put in this category. The performance quality of LTSA is very close to MLLE and HLLE. However, it runs much faster on the 10-digit dataset, as you can see. Hence, in our problem, it's preferred to MLLE or HLLE all the time. It is safe to conclude that this method shines when it comes to large datasets compared to those other LLE methods. We give this method an A+ grade because of its acceptable performance and a good runtime. Our runner-up is TSNE. TSNE is the best algorithm in this list when it comes to performance and the clear-cut classification of the digits. There are clear boundaries between the digits, and classification is great. But don't forget, we have initialized this algorithm by an embedding generated by a PCA to ensure its global stability, of course. As we can see, there are some mistakes in classifying digits 1, 8, and 9, but they are not a deal breaker. TSNE is also the slowest algorithm in this list. The great performance, yet the much slower runtime and high complexity is why we give this method an A grade. The winner of this competition is MDS. MDS seeks a low-dimensional representation of the data in which the distances respect well the distances in the original high-dimensional space. MDS is one of the slower methods of this list, yet it's not the slowest, and it performs quite well compared to others, but it's not the best. The distinction between 2 and 3 is remarkable, but in the case of 10-digit dataset, it's not doing very well, the digit 1. The good performance A good runtime will give this method an A++, and it is the winner of this competition. And this is the overall comparison of the methods. For our problem, LLE is the worst, and at the same time, the fastest one. TSNE is the best when we talk about performance, but it's the slowest method. Overall, MDS method shows good quality classification while not being that slow, and it is our choice for this problem. In the end, thank you for your attention, thank you for consideration and your time.